All right, I wanted to say a few words about the plan for next week. So I've got the Parts Cleaning Conference in Chicago. Pretty excited about this. It's at the International Machine Technology Show, IMTS. And you've been to the George R. Brown Convention Center in Houston, maybe? Big place, ever been there? Okay, it's where they have these huge exhibit halls and vendors bring their equipment and set it up. You walk the show floor and see all of the things that they have to offer. And you might imagine that machine technology, like huge CNC mills or robotic systems for moving parts here and there, and things that plug into like conveyor belt and assembly lines, all of this machining technology. It's such a large show that it's about 4 times as large as the George R. Brown in Houston. Yeah, and so then all of those companies that make things have to also clean them. And so that's where we're having the Parts Cleaning Conference. And so I'm the co-chair of the conference. And so I'll be introducing the speakers and everything like that. So that's going to be exciting. That's on Tuesday. So I got to fly up there Monday, fly back on Wednesday. So I'm going to miss Monday and Wednesday. So what are we going to do? Well, here's next week. Here's Monday. These videos are already in the week 4 folder. So you can watch them. They're very current. They're last year's videos, but they use the same handouts. And so just treat it just like you're in class. Get your handouts printed out, go through, fill out the blanks and everything like that, and prepare for the exam. Still, though, mentally, anxiously, and so on, I know that it will cause some students to panic, to think that they're going to finish out the material and take an exam without me. Okay, because I know if you were like, well, are we still having you're going to be gone? I could just sense the angst. So here's what I'm willing to do. We got to negotiate, right? So here's what I offer. If we move the exam to the next Monday, okay, it'll put us behind, and I don't want to be behind. This is also a video lecture. So if we do the exam on Monday, will you watch this video lecture, and then we'll stay on track? And so after the exam, sometime that Monday, switch gears, download the notes, go through that next lecture as if we had Monday class, and then we'll be back on track. Does that sound good? And then I can answer all your questions on Friday. So you go through the material. We can go all the way back to the beginning of the semester with questions, all of the homeworks and everything like that. We can have a big study session on Friday. Then we'll do the test on Monday. You guys watch the lecture, Monday's lecture. So then Wednesday we'll be back on track. Wednesday, 2 weeks from now. And this says watch video. We'll actually be live there. So we'll be live on Wednesday, and you will have watched the Monday lecture. Otherwise, the Wednesday lecture won't make a lick of sense. Okay, and then we'll be back on track. Now, the scary part then is this next material, the numerical simulation stuff, is just as a test on essentially 1 week of material. So we're going to have exam 1, and then a week of material, and then exam 2. Okay, so it's just I just think that that's the best way to sort of test and break the material up. It's not necessarily even, but it's really conceptually very different. And so we'll just have a numerical and Gaussian type simulation exam focused on just that material. It'll be a pretty easy exam because there's not going to be a lot on it, and so you can really grasp the material. So we're going to have 2 exams here in the next 3 weeks. But I want to make sure that you go into this Monday exam confident, so we'll have a study session on Friday. So I won't see you for a whole week. I'll come in here. You will have prepared with lecture 9 and 10, and you'll have good questions for me. We'll hammer through all of that, and then we'll be ready for the exam on the following Monday. Sound good? Okay, I see lots of nods, so that's great. Okay, so today is pretty exciting. We're going to use the character tables. So they're printed in the lectures, but if you have the character tables, it'll be nice for you to have the C2V character table kind of over on the side so you can see with your own eyes up close what we're looking at. So here we are in the need for symmetry. If we've taken a molecule like water and we've done the Vesper shape, so we've made our molecule, we've got the lone pairs. It's a bent molecule. This is, 109.5 degrees roughly, because there's 4 electron domains. etc. So then we end up with this molecule. We draw the coordinate system. So the z-axis is that C2 axis. We run this molecule through the character table. Also, the right-hand rule, let me show you this. So everybody hold your right hand, put the thumb up, that's the z-axis. Point with your index finger, that's the x-axis, and your other fingers go out, or your middle finger goes out, that's the y-axis. So that's the right-hand rule. All of your coordinate systems are going to be right-handed. It's nothing to do with, there's no moral component to that, right? It's just somebody had to decide how to do physics. And so they said, all right, let's have this right-hand rule be how we set up our coordinate systems. And that's how the character tables are made. So if you do a left-handed rule system, notice it's a mirror image and they're not superimposable. So that's going to be a problem. You'll have everything backwards. And so we're all going to agree to use a right-hand coordinate system because that's how the character tables are made. So what does a right-hand system look like? Well, if I'm looking at my thumb as the z-axis, then my index finger comes out, that's the x-axis, and the other finger is the y-axis. Okay, and you could look at it this way. If you draw your coordinate system like this, it's kind of a counterclockwise x, y, z, x, y, z. Does everybody see that? Okay, you're going to get lots of practice on this next week's lab. Okay, so we're going to be in the lab session. Your next week's lab's all handwritten. You're going to draw molecules. You're going to draw coordinate systems. You're going to assign character tables. If we take this molecule through the character table, we end up with C2V is the point group. And so this is going to be what you will draw next week. You'll draw a molecule. You'll draw a coordinate system where the z-axis is lined up with the symmetry axis with the biggest number. Okay, so if you have like a C3 and a C2, you're going to pick the C3, and that's the z-axis. And then you have your coordinate system with x and y. Okay. And then you find the point group, put it in a box. Now, if you draw it just like this, the TA will know you know what you're doing. All right. So once we have that point group, then we know what character table to use. So this is where we are now in this whole symmetry system, is using the character table. The character table determines the symmetries of the molecular motions and the molecular orbitals. And we won't apply this in this class, but still you could use it to determine equivalent nuclei in NMR. Okay, but we'll do these top two for sure. Even today we'll do both of those. Then we'll get into direct product tables in the next lecture. So next week you'll be dealing with the bottom two bullet points. So this is the character table. It's a little bit of review from the last lecture. The actual blue part is the character table. Okay. And you have the point group, the CHEM notation. So for water, this is C2V. And then these are Milliken notations. They're called irreducible representations. We talked about the sort of their independent rows, like in a linear algebra manner. And then over here, we have the characters in the middle. And then we have these Cartesian and rotational basis functions. That's the symmetry of all your axes and all the second order combination of axes. You could, for orbitals, you could think of these as your p orbitals. And these as your d orbitals. This is also the Cartesian axes. And we'll see today it can also represent different kinds of vibrations and rotations and so on. So these are the rotational functions. The R stands for rotation. So this is rotation around Z, rotation around Y, rotation around X. So let's look to see how all of these things are compared to the molecule and their molecular motions. So here are all of the things that a water molecule can do. So let's introduce this concept of degrees of freedom. So think about just a particle in space. it can move in the x direction without changing its y coordinate or its z coordinate. Does that make sense? So x and y and z are independent of each other. And so those are independent degrees of freedom. That's how you can, how the atom can move in space. It's free to move in x without changing y or z. It's free to move in y without changing x or z. And so every atom has 3 degrees of freedom. Well, if your molecule has 3 atoms, then each of those atoms still has 3 degrees of freedom. But we classify their motions because they're connected to each other. We classify their motions a little differently, okay? If all 3 atoms move in the same direction, then the molecule can stay intact, right? So if I've got a water molecule and all 3 atoms move in the x direction coming out of the plane, then the whole molecule is still, this bond length hasn't changed, the bond angle hasn't changed, the whole molecule is just translating in the x direction. So that's translation. If all 3 atoms move in the y direction, that's translation of the whole molecule without changing bonds or angles in the y direction, and same with z. Notice how for translation, there can only be 3 translations because all 3 atoms have to move in exactly the same direction. And there's only 3 ways to do that. They can all move in the x direction, the y direction, or the z direction. Make sense? There's only 3 ways you can translate. And so that's why if you look at these top 3 rows, those are the 3 translations for water. The x is kind of hard to see. What I've done with these arrows is I've tried to line them up with the x-axis, okay? We draw that x-axis diagonally down, but it really is meant to come out. It's like perspective. It's meant to come out of the plane of the board. And so these arrows, even though they look like they're going down and to the left, they're really coming out at us. We could draw a wedge here like that. So x direction would be out of the plane of the board, and the whole molecule is coming towards us. Y direction, notice here's the Cartesian system, and all 3 of those atoms are moving in the y direction, so that's y translation. And then here they're all moving in the z direction, so that's z translation. So of the 3 n total degrees of freedom, 3 of those are translation. And I'm going to say always 3 translations, and only 3 translations. Even a big molecule, DNA, what can it do? 3 translations. You got so many atoms, but it can still only move in the x direction by itself, y direction, or z direction. What if half the atoms move in the y direction, positive y, and the other half of the atoms move in the negative y? Well, if the molecule is going to stay together, that's rotation. So if you don't change the bond lengths or angles, and you get you bump half the molecules, you get it to spin. And so then that would be different. That's not translation, that's rotation. And so that if you spun that molecule around the x-axis, then that would be the Rx. And if you spun that molecule around the y, that would be Ry. And if you spun it around the z, obviously it'd be Rz. Now there are 3 rotations for a nonlinear molecule. The reason we specify nonlinear is pretend this is a molecule that it's infinitely thin, that there's nothing on the no thickness to it, right? I could tell if the molecule spins end over end in this plane. I could tell if it's spinning end over end on this plane, but I couldn't see it spin around the z-axis if it's a linear molecule. There's nothing off axis. Another way to think about that is there's no angular momentum. There's no mass that's off axis. So there's no way to know if it's spinning. There's no energy associated with that spinning. It's just not defined because there's nothing off of the axis, so you wouldn't know that it's spinning at all. Okay, so there's no rotation. If that's the z-axis, there's no rotation around the z-axis for a linear molecule. So there's only 2 rotations for a linear molecule. Let's write that over here. Only 2 rotations. And that would be Rx and Ry. For linear molecules. So aside from that caveat, 3 of our total degrees of freedom for water are rotations. Now, in general, for molecules, you're going to ask, or I'm going to ask you, how many vibrations does this molecule have, right? If I give you benzene, and I say, how many vibrations do you have? Well, benzene has 12 atoms, and so 3 degrees of freedom for every atom. That's 3 times 12, or 36 degrees of freedom. But benzene still only has 3 translations. It's not linear, so it has 3 rotations. And so the vibrations are always 3n, that's the total degrees of freedom, minus 6, minus the 3 rotations, minus the 3 translations. So this is always the number for the vibrations of a molecule if it's nonlinear. Okay. And over here it's 3n minus 5 if linear. Do you see why it's 5? Where did the 6 and the 5 come from? Yes, so that's the definition of a vibration. It's anything that's not a translation or a rotation. So you take the total degrees of freedom and we take out the translations, that's 3 of them. We take out the rotations, that's 3 for nonlinear and 2 for linear. And the rest is vibrations. So for benzene with 36 degrees of freedom, we take out the 6 because it's nonlinear, and we have 30 vibrations. So we have 30 potential peaks in the infrared spectrum. So this is why we want to know that. We want to know how many potential peaks would there be. You see a really complicated infrared, you count up 48 peaks, and you have benzene in there, you're like, can't be 48 independent vibrations. It only has 12 atoms. So only 30 of those peaks are benzene peaks. I've got an impurity. So that's a way you could use that information. Okay. And so then down here we have, we get to assign today Milliken notations to all of these motions. Notice I haven't talked about A1, B1, B2 or anything like that. That's what we're going to do today. So determining the Mulliken notations for these, for the top 6 are really easy because it's either X, Y, or Z translation, or RX, RY, RZ rotation. And then the bottom ones, the vibrations, are easy after today. So that's what we're going to cover is the vibrations. But let's first talk about the translations. So if we just go back to the character table, let's look at this X translation here. So whenever I see the whole molecule moving in the X direction, I go back to the character table and I find X. And then I come right over here, and then that motion of that molecule is labeled B1. So that's the symmetry of that translation. So that's why we label it B1. The Y, if we go back and find the Y in the character table, it's going to be on the row B2. And so then that's where this came from, this B2 came from, because that was where the Y was in that character table. And then if we go back at the character table and look up Z, Z is on the top row, right here. And so that's going to give us A1 for that motion. So translation in the Z direction is A1. The RX, RY, and RZ are just as obvious, right? Let's go back to the character table and just see those all together. So RX will be B2. So that's rotation around X, rotation around Y is B1, and rotation around Z is A2. So that's a unique one. Rotation around Z is A2. And so that's what we have. Rx is B2, Ry is B1, Rz is A2. So those are easy. You just go to the character table and look them up. The stretches are not as easy, okay? Hopefully, well, I guess that's the point of the course, for you to look at these little arrow diagrams. See, what we've done with the arrows is we've tried to show the motions of the atoms. And down here we have 2 hydrogens being pushed down and out, and the oxygen moving up. Remember, we can't move the center of mass. If we move the center of mass, then the molecule's translating. So all of the vibrations, the molecule is still in space, and just the atoms are moving against each other. So if we stretch those bonds, we got to move the oxygen up just a little bit so we can stretch those hydrogen bonds. Think of it as springs or bungee cords. If I pull down on those bungee cords, it's going to pull the oxygen down. So there needs to be a force that pulls the oxygen up a little bit. And then when I release them, they're going to snap back and the oxygen's going to snap down. And so then just run a video of that, and that's the symmetric stretch. So the hydrogens are stretching down and the oxygen's moving up just a little bit, and you have your little video of the molecule stretching. Why is it symmetric? Well, it's because both bonds lengthen. Okay, let's look at the asymmetric stretch over on the right. One bond shrinks while the other one stretches. Now, if I do that with my bungee cords, the oxygen's going to want to go that way. So I need to move the oxygen in the opposite direction so that the center of mass doesn't move. So the oxygen opposes that motion a little bit. It moves to the right while the hydrogens move to the left, and then you snap it back and run the video, and you can see that oscillation. So if my head is the oxygen and my hands are the hydrogens, this is the symmetric stretch. Okay, and this is the asymmetric stretch. Okay, and then the symmetric bend is just changing the angle. So if we just change the angle between the OH bonds, notice how these are three independent motions. They're three vibrational wave functions is what we're describing, and they're orthogonal to each other, meaning I can change the angle without changing the bond length. So they're independent of each other. Now that's a graduate course in itself, trying to figure out how to determine the normal modes of vibration. So you're just going to be given those. Like, you didn't determine these arrow diagrams, but in the graduate class, spectroscopy, we'll go through what's called the projection operator, and you'll actually determine the little arrow diagrams. So it's really cool. But right now, we'll just give them to you, and you need to figure out their symmetries. So given those arrow diagrams, let's figure out their Milliken symmetries. Okay, so here we are. This is one way to do it. It's called the component vector cancellation method. So do you remember back in the day, I don't know what grade it was in, but it was a part of algebra where you added vectors. Like if you had a particle that was pushed on in this direction, and then it was pushed on in this direction, where would the particle end up? It would end up right here, right? You can add those vectors head to tail, and this is the motion of the particle, right? So these were called component vectors, and this was the resulting vector, okay? These black arrows, let's treat those as resulting vectors, and let's use our Cartesian coordinates as the directions of all the component vectors. So this is in the plane of the paper. There's no wedges or dashes here. So this arrow, this oxygen arrow, is going straight up, and that's along the z direction. So let's just draw all the z component vectors. So along z, we have the oxygen moving up, and the components of hydrogen in the z direction are going down. You see, if that's that angle, that diagonal is the resultant vector, the component of the z direction is going down. And then let's draw the y component. So you look at your horizontal axis, and we would draw horizontal component vectors. And those, for those hydrogens, would go out. Both of them would go out. So we've taken our black arrows, our resultant vectors, and broken them into Cartesian components. And so we just have a z component and a y component. They're all in the plane of the paper, so there is no x component for this motion. Okay? Before we go on, I want to make sure that everybody's clear on how to do this piece. You just take where your Cartesian axes are, and you draw these vectors that are parallel. So this vector here, this blue one, is parallel to this z-axis. You see how we're doing that? So everywhere there's an arrow, you draw a little z component, and then this resultant goes from tail here to head here, and so then that's how I know that the head of this z component is down. It's like, what's the path? If I want to go from, 75th Street and Avenue H, and I want to go to 76th Street and Avenue I can't go through the building. I got to go down this street and over. Okay, so that should help. All right, now let's look at the results. The x vectors are going in opposite directions, and so they cancel out. I'm sorry, x, I meant y. The y components cancel out because they're in opposite directions. The z arrows are going in the same direction for the hydrogens. and they don't cancel out. And so that means there's going to be a dipole moment that's set up going up and down. The hydrogens are positive, okay, a bit positive. We'll do our little deltas like we did in organic, right? Remember that? We were just talking about that. And if that bond length gets longer, at least that going down, then you see that we've increased the dipole moment a little bit. We've separated the charges a little bit. So this dipole moment has gotten stronger. And guess what? That's what light can interact with. So light is an oscillating electric field, and if the oscillating dipole moment in water matches that frequency, then we've got a good match. We can absorb that photon of light. So this is how water would interact with light, by changing this dipole moment. Water's not charged. And remember, that was one of the requirements we had for interacting with light, that you had a charged particle, or the caveat was, or a change in the charge distribution. So this changes that charge distribution a little bit, enough for light to interact with it. So we have a Z component that's unchanged, that changes with this vibration, and so then this motion will be on the Z row of the character table. So we can look up there, find Z, and find A1. So the Z components don't cancel. Cancel. Giving a changing or oscillating is there two L's in oscillating? Dipole. Right there. And that dipole is oscillating in the Z direction. So because it's oscillating in the Z direction, it will have Z symmetry, which is A1. I see you writing, so go ahead and think about what you're writing down, and then make sure I can clarify anything that you're confused on. We'll practice the other motions, and so we'll get another couple of examples. Okay, let's look at the symmetric bend. It's also Z, but we'll see how that works out. Okay. Same kind of thing. We look at that Z-axis and we draw all of our Z component vectors that are parallel to that Z-axis. This time the Y direction component vectors are going in. The last time they were going out. But they're still opposite of each other, so they cancel. So those Y motions cancel, and we still have an oscillating dipole that is going up and down on the Z-axis. It doesn't ever flip direction, but it gets stronger and weaker. And that's enough. That's the larger the change in dipole moment with the vibration, the larger the intensity in the transition. Okay, but this is enough for this motion to be infrared active. Okay. And so then that dipole moment is set up along the Z-axis, and so it's going to be A1 symmetry. So this one was so similar to the other one, I went pretty fast. The next one's going to be much more interesting. Okay. So let's look at the asymmetric stretch. So there's the symmetric stretch, which we did first. This is the asymmetric stretch. Why is it asymmetric? It's because one bond length gets longer while the other bond length gets shorter. Okay. You can write this as, let me just up here put psi vibe is equal to, and we're going to call this R1, and we're going to call this R2, is equal to R1 minus R2. Okay, so the sign in front of the bond lengths just sort of a notation here. R1 minus R2. It means they change. I'll put they. I said the. Means they change in an opposite manner, right? When R1 gets big, R2 is opposite of that, so it's going to be getting smaller. Let's go back and label the symmetric stretch. Okay, the symmetric stretch. This is sort of extra stuff that will help us later. Psi vibe is equal to, and if this is R1 over here and R2 over here, what do you think the symmetric stretch is? R1 plus R2. There'd be some coefficients in front of that to represent normalization factors and things, but this would be a shorthand for writing the vibration in terms of the bond lengths. This is the vibrational wave function shorthand, if you will. Okay, so then the asymmetric stretch, this vibration is just equal to theta, right? We're just changing theta. And so we're just, the wave function is the change in theta, no change in R1 or R2. Now, if I want to specify the structure of water, those are my three variables that I have. 2 bond lengths and an angle. And the vibrational motions would be the changes in those internal parameters, bond lengths and angles. Okay. So let's look at this asymmetric stretch, component vectors. So we do the z-axis again. There's only 2 z components, and they're on the hydrogens because the oxygen's moving in the y direction only. Okay? So we have an up and a down. And now let's do the y components. The oxygen's moving in y, and the hydrogens are moving in y. They're moving in opposite directions. Okay? And can you see now it's the z components that cancel? One z is going up, the other z is going down. So we're looking at the vectors that don't cancel, and those would be the y directions. So if the hydrogen, if this delta negative gets closer to this this delta positive gets closer to this delta negative, then the charge difference gets smaller on the right, and it's going to be overwhelmed by the negative of this oxygen, and then we're stretching out this one. So you see how the dipole moment is set up where it's positive on the left and negative on the right as we have the asymmetric stretch. And then we run the video, and now the hydrogen stretch and compress in the other direction, and this dipole moment actually changes direction. So this dipole moment, this will be a really strong transition in the infrared because the dipole moment flips over. It's pointing in one direction on the y-axis, and sometime later it's pointing in exactly the opposite direction. So this would be the y symmetry row, and so you go find that in the character table, and it's B2. Straightforward? Okay, that's how you take the arrow diagrams and turn them into the Milliken symmetries out of the character table. Okay. And whenever you have simple directions like X, Y, and Z, it's super easy. It can get a little bit more complicated when you have, let's say, let's see if I can think of a Z2B molecule that's planar. Yeah, let's make up a compound. Platinum, it makes a square planar complex, and let's put bromines down here. Okay. And so this is a C2V molecule. Just it kind of looks like water. I don't know. And to me, it looks, the left and the right are the same. The front and the back are the same, but the top and the bottom are different. That's one way to think about water. Okay. And what if we had components where this bond stretches, and this bond stretches, and this bond compresses, and this bond compresses? Okay, that's kind of a strange pattern. And here we have the y-axis and the z-axis. Notice how this bond gets larger, so that's going to be a plus. And notice how this bond gets smaller, so that's going to be a minus. This bond gets larger, so that's a plus. And this bond gets smaller, so that's a minus. This is one of the more complicated patterns, but when you see it in the future, you're going to be like, yes, I recognize that. Okay. What if I were to plot the function y times z. So if my function is y times z, I have y here and z here, what are all of the numbers in this quadrant here? If my function f is equal to y times z, and I'm going to plot all of those numbers on this plane, well, all of these numbers up here are positive y times positive z. So they're positive. And all of the numbers in this quadrant are positive z, but they're times negative y. And so those are negative. And down here, the negatives cancel. I've got negative numbers in the y direction and times negative numbers in the z direction. And so those are going to be positive numbers. And then down here, I have positive y numbers times negative z numbers, and I end up with negative numbers here. See that plus minus pattern? Anytime you see that, whether it be bond stretches or colors on a molecular orbital, that is xz, yz, or xy. It's one of these. So if we were to see this kind of vibrational pattern, we would know that that is y times z, and it would be this one right here, and it would be B2. So it can get a little bit more complicated, but that's probably one of the most complicated. So if you kind of follow that halfway, we'll get more experience with it. But I just want you to feel comfortable with the arrows, trying to think of them as if they're growing away from the center of mass, that's like a positive. If they're shrinking towards the center of mass, that's a negative. Molecules getting smaller in that area. Whereas if they're stretching out, it's molecules getting bigger in that area. So that's, you can think of that as a positive. Remember, we're dealing with deflections, not charge in this case. So stretching bonds and so on, there may be some charges related to that, but wave functions are about deflections from the average. So think of the slinky. You know, if it's staying in the middle, that's the average. If it's deflecting up, that's positive. If it's deflecting down, that's negative. So it's deflections from the average. Okay. So this is the way the vibrational energy levels look if we have particular symmetries associated with those motions. This is the harmonic oscillator model. And so down here, we might have like the oxygen here and the hydrogen, and it's oscillating in and out. So the oxygen atom and the hydrogen, and it's oscillating in and out. Now that would be for a diatomic. For the polyatomic, it's all of the coordinates of all three of those atoms changing, but it's still a one-dimensional vibration. And so the ground state of those vibrations are even. If you think about the wave function for the ground state for the particle in a box, it looked very similar to this. This would be the vibrational ground state. It's a Gaussian function. And surrounding zero, it's an even function. This one is also even. It looks like that. Very similar to our particle in a box. Let's see if I can do this one. Yeah, it goes up, down, up in the middle, and then down, up, down. I had to burn a brain cell to get that. Okay, so these are even as they alternate going up. And so even numbered quantum states in the vibrational system starting at v equals 0 have top row symmetry. And so I say top row symmetry because in some character tables that would be AG, some character tables would be A1G. In this C2V character table, top row symmetry is A1. So we see A1 every other level going up. The odd number quantum states in vibration match the symmetry of the motion. So remember our symmetric stretch was A1, but our asymmetric stretch was B something. Can you look at your notes? B, was it B1?
Asymmetric stretch, B2.
B2, okay. That's going to show up here in a second. The symmetries of the asymmetric stretch were B2, and so that's the odd numbered vibrational quantum states have the symmetry of the motion. And so if this particular potential energy function is for the asymmetric stretch, then it would be A1, B2, A1, B2, A1, B2. Okay. So now we know the symmetries of the energies, and in the next lecture, we could solve for the transition dipole moment integral for water. A big leap away from the particle in a 1D box. but the same skill that we learned with symmetry. Okay. Molecular orbital wave functions do not alternate in a regular pattern. So put a star on that. A lot of people think that this is how it behaves for everything, but this is for vibrations, okay? And rotations also behave this way, but MOs, molecular orbitals, do not alternate in a regular pattern. Let's look at some molecular orbitals. So let me comment, because this is going to make you freak out perhaps. These are the molecular orbitals, but you don't know where they came from, okay? And that's okay. What I do with my teaching is a sweeping motion. You make a real quick pass at the material, and then you go back and sweep again. And then you go back and sweep again. So I'm giving you this with just out of the blue. Now, you've seen molecular orbitals in organic and so on, so hopefully you're kind of comfortable with that. But think about these molecular orbitals like you thought of the vibrations. You're very comfortable with the vibrations of atoms, right? This is this oscillation of the electron cloud. So around that ammonia molecule, we have red color. Okay, let's say that red means expansion. So that's telling me that whole cloud is expanding in all directions. What's that cloud going to do a few seconds later? It's going to turn green a few, like, femtoseconds later. It's going to turn green and shrink. And so when we think of an s orbital, it's not just a ball, it's an oscillating ball. It's getting big in all directions and shrinking in all directions. What do we think of with a p orbital? If we draw a p orbital, okay, it's going to be shaded on one side. We'll say this is the red color. That means that side is expanding while the other side shrinks. And so the electron cloud in a p orbital is doing this. So does that make those pictures kind of come alive in your mind? That also means there's a change in the electron cloud distribution. So there's going to be dipoles and things set up as well. So it can interact with light. So the molecule is not charged, but there's a change in the charge distribution in the y direction. And guess what? Y polarized light's going to interact with it. So if you can look at these clouds and see how they change, you can figure out their symmetry. That's the point, okay? So in this particular set of orbitals, here's the character table for ammonia, C3V. Here's the coordinate system. The symmetry axis is that C3 axis coming out of the top of the molecule as it's drawn. And so the x direction, let's just look at this one. This cloud is getting bigger in the x direction, while this one shrinks in the x direction. Look at that picture and try to get in your head that all of those off-axis arrows, the directions of y and z would all cancel out, but the y direction wouldn't. The cloud is moving left and right in the x direction. Can you see that? If you can see that, you're doing great. See, this whole cloud is getting bigger in this direction. This whole cloud is shrinking in that direction. Sometime later, they're going to change color and do the opposite, because otherwise our electrons are going to get stripped off our molecule. All those nuclei are drawing those electrons back, and they'll just splash the other direction. So this is splashing in the x direction. So all you got to do is come over here and find x. And we'll see that that's E symmetry. So this one is E. Let's look at this one, splashing in the y direction. So we come down here and find y, and that's also E symmetry. Now what does that tell us? That tells us these have the same energy. This is a degenerate set of orbitals, and so in our energy level diagram, we're going to have two orbitals. One of them is going to be the x molecular orbital, and the other is the y molecular orbital. And then down here, this is in all directions the same. What's the equation for a circle? Do you know that? So if I was to plot a circle in the x, y plane. What's the equation for that? Do you remember from algebra? It's taking you way back. The equation for a circle. X squared plus y squared, exactly. X squared plus y squared is the equation for a circle. Okay? And that is just an expanding circle of it's the same in all directions around the x and y axis. And that's, you find that right here. That's x squared plus y squared. It's essentially that circle of an electron cloud getting bigger in all directions and smaller in all directions. And so that's going to be A1. And so this one will be A1. And so down here, this will be a lower energy. That'll be the A1 orbital. The x squared plus y squared. It actually has a z squared component as well. But so we can write out the energy level diagrams. How do I know that these two are higher than the other one? Why are these higher? I'll say energy. How do I know that those two orbitals have higher energy than the other one? So energy, I'll just say this, is proportional to the second derivative right, which is curvature. So if I have a wave function that's more curvy, it goes up in energy. How do I know that those top two wave functions are more curvy than the bottom one?
Because there's two separate lobes.
Lobes and nodes. You got it. The lobes and the nodes. So right here, there's a node in the middle. And here there's a node over here. And so these, why higher in energy? Because more nodes. So just like in our particle in a box, the ground state wave function had no nodes. The next wave function had one node. The next one had two. So as those wave functions get more curvy, they go through zero more often, and you have more nodes. And so this is this three-dimensional node. I mean, it's a plane, but you can see now in space you can have a node, just like on a wire you could have a node. So we can get to water. Here's all of the molecular orbitals for water. And I would love for you to go through on your own and find out why these symmetries are correct. Okay, do you see the symmetries of the wave functions here? Compare those pictures to the character table, and the only one that's weird is this one right here. Let me just go to the next one. For this picture right here, we've rotated the molecule. See where the hydrogens are? So the coordinate for this one, Z, X, and Y goes into the board. Okay, so for this one, we've rotated it just so that you can see the nodes and the lobes a lot better. Now, I went a little long on some of the earlier pieces, like the component vectors, and so you may want to watch last year's video on this, where I go through this next few slides in detail. So you can scroll through that last year's video up to this point, and then pick up the last 5-10 minutes, okay? That'll help. Because I talk about this little flow chart, and this flow chart is pretty helpful. We did everything in this flow chart, but I didn't teach you the flow chart. Okay. All right.